Okay, we've got a new momentum problem here. We've got a satellite out in space. Let's see if I can draw a nice picture of a satellite here. And there we go, there's my satellite. And the satellite shoots out from this back thruster. It shoots some gas, okay, and that gas is moving very fast. Now, before the satellite shoots the gas, the whole satellite, the whole mass of the satellite and the gas put together. So maybe it's a better idea if I actually draw a picture of like a before and after. So how about here's my before picture. Okay. And there's the gas inside of it. The total mass of the satellite is 225 kilograms. Now, 225, of that 225, the amount that comes out, the mass of the gas that gets blown away, is 10 kilos. Okay? The satellite is originally traveling to the right, here in space, with a velocity of 350 meters per second. The question is, after the gas is ejected out at a speed of 2,000 meters per second. Okay, that's how fast the gas is going when it comes out to the left. What is the new velocity of the satellite? That's what we want to know. So the way we're going to do this is we're going to use conservation of momentum. We're going to say pi equals pf. And we're going to say, okay, how many, so this is the before state. Well, let's write that here. And this is the after state. Question now is, what was moving before the explosion? Well, you had the mass of the satellite and the velocity of the satellite beforehand. Afterwards, you have the mass of the gas and the velocity of the gas plus the mass of the satellite. But you know what? I'm going to do something that you don't usually see on a mass. I'm going to put the final mass of the satellite here multiplied, and usually you don't because the mass doesn't change, but in this case it did, times the velocity of the satellite after. Okay? So that's my conservation of momentum equation. Let's see if we can put some numbers to this. Originally, the mass of the satellite was 225 kilos. Okay? The velocity of the satellite originally was 350 meters per second. Then, what's the mass of the gas? Well, that's given as, right here, 10, okay, multiplied by the velocity of the gas, which, now listen, if this direction is positive, that means that this 2,000 being to the left is a negative 2,000 meters per second. Okay? Plus, let's make some more room here. Now, here's the interesting part, is what is going to be the final mass of the spaceship? Well, listen. You see, the original mass of the spaceship, correct, was 225 as we see here, but 10 of that is lost. So really, in this case, it's 215 because it's 225 minus 10. So we've got 215 kilograms now left in terms of the mass of the satellite, multiplied by the final velocity of the satellite, which is, by the way, what we're looking for. So if we did this now solving for Vs prime, we're just going to go 225, and I'm going to drop the units so I can make this cleaner looking, times 350 divided by, or sorry, not divided by. First we have to subtract. Yeah, okay, let's just subtract it here. And then we divide all that by 215. And so we're going to get, using our trusty RPN calculator, 225, enter 350 times, and then 10 times 2,000 is 20,000, but that, that becomes now plus. And 215 divided by, giving me an answer of 459.3, almost 460. 459.3 meters per second, which is the final velocity of my right. So we've got, this is now equal to 459.3 meters per second, and that's what we were looking for. And that's the end of this problem. Hope you enjoyed it. Bye.